Hello, good morning, good evening, good afternoon, everybody, wherever it might be. We are very happy to have a speaker from Colorado Spring. MESYAN will tell us everything and more about posets from Leavitt path algebras and graph inverse semigroups. Zach, it's all yours. Take it away.
Thank you, Piotr. Thank you for the invitation. So this is an unusual talk for me because I've never talked in a non-commutative geometry seminar and I've never attempted to give a 90-minute research talk. And so this is a bit of a compromise. The first half is going to be something of a literature overview. And the second half, I'll talk about Leavitt path algebras in particular. And most of the stuff that I'll mention isn't very cutting edge at this point. You know, some of it is older, but I thought for this particular audience, this would be appropriate. So that's the thinking. Um, so I know you've had some talks on Leavitt path algebras. I want to get to those, and I want to talk about graph inverse semigroups. But I thought that what might be more familiar for the typical audience here is graph C-star algebras. And so I thought I would start there. So all of these objects that I mentioned, they're built from directed graphs. And I put some graph terminology here, which I won't go through, just not to bore you, but I put it here for reference, and then I'll mention some of these things as we go along. So let's say you start with a directed graph. You can build a graph C-star algebra, and very roughly the way you do that is to every vertex and every edge you assign a function, and then you generate the universal C-star algebra with that, with some relations. And a lot of the work here is done by properties of the function. So some of them are required to be projections and orthogonal and so on and so forth. And I know very little about graph C-star algebras, so if I get anything wrong, apologies. But I understand that this was introduced as a very nice class of C-star algebras that can be worked with, and this definition goes back 30, 40 years and includes some very well-known C-star algebras as well. Matrix strings over the complex numbers, complex values, continued functions on the unit circle, Kunz algebras, and compact operators on separable infinite dimensional Hilbert spaces. Okay, so that's a graph C-star algebra. Now, I'm an algebraist, and when I see something like that, the first thought is, what happens if you strip away all the analysis and the topology and that? What do you get? Well, you get a Leavitt path algebra. So here there's no functions anymore. We just start with a field, and this time it can be any field, doesn't have to be the complex numbers, and it can even be a commutative ring. But we'll stick to fields for the current purposes. So you take a field, you take a graph, and then you just generate an algebra using the vertices and the edges. But now, if we want to preserve some of that structure from before, we have to compensate for the fact that we no longer have an adjoint. And so the way we do this is we throw in these ghost edges that are denoted with stars. And then we try to keep as many of those relations as we can, particularly CK1, CK2. And then there are a few others to make up for the fact that we were not talking about orthogonal projections anymore and whatnot. So that's my understanding of what happens here. And you get a very nice class of rings. In it, it's very easy to write down a normal form for an element. So every element is a linear combination of elements of the form PQ star, where P is a path in the graph, and Q star is made up of these star edges or ghost edges. It's a ghost path, as it were. Um, and here, one nice thing of thinking of it this way is that the star bit, it's not quite an adjoint in the same sense as before, but you can give it graphical meaning. And we can think of taking the graph and kind of extending it. It's called the extended graph with these ghost edges. And visually, this is what it looks like. Say you start with a directed graph, and then for every edge, you introduce an edge going in the opposite orientation between the same two vertices. Those are the ghost edges.
Mhm.
All right. So, and this also gives a very nice class of rings. This definition goes back about 20 years. it appeared in two different papers that were written around the same time, but published 2 years apart. And we get matrix rings now over all fields, and we get the Laurent polynomial ring, and then we get the Leavitt algebras. This is where the Leavitt part comes from. So in the 1960s, Bill Leavitt studied these things, and they have this universal property that the nth Leavitt algebra coming, if you think of it as a Leavitt path algebra, it comes from this graph with one vertex and n edges. And the nth Leavitt algebra, if you take a product of n copies of it, that's going to be isomorphic as a right module to just one copy. But if you take somewhere between 2 and n copies, strictly speaking, then you won't get anything isomorphic. So that's what happens there. And notice some of the same graphs come up here as they did in the C-star algebra case, but they give you slightly different things, and they have a somewhat different history in the ring theory literature. All right, so that was um, graph C-star algebras and Leavitt path algebras. So how did we get to Leavitt path algebras? We took graph C-star algebras and we threw away the analysis and the topology and all that. So what happens if we throw away the algebra too? If you look at the definition of the Leavitt path algebra, there are 5 of these conditions, and 4 of them involve only multiplication. And the last one is the only one that involves addition. So we can just get rid of that, and then what we end up with is what's known as a graph inverse semigroup. So here, yeah, it's just the graph, and you generate a semigroup using the edges and the vertices, and we still want those ghost edges, but now I'm denoting them with inverse notation, not stars, for reasons that I'll explain in a second. But otherwise, the defining conditions are the same, except we threw away the one that had to do with addition and just kept the multiplication ones. Just like in Leavitt path algebras, here we have a normal form for every non-zero element. It's of the form PQ inverse now, where P is a path and Q is a ghost path, as it were, made up of these inverse edges. Here's where the inverse part comes in. This is an inverse semigroup. In case you haven't seen this before, it's something between a normal semigroup and a group. And in such a thing, every element has a von Neumann regular inverse. So for every x, there's a y, so that x, y, x is x, and y, x, y is y. And in this particular thing, if you take a non-zero element PQ inverse, its semigroup inverse is going to be QP inverse. And so that's why we use this notation. So if you've never seen this before, you might think it's some kind of ripoff of graph C-star algebras and Leavitt path algebras, but it's not. And I'll explain that in a second. First, how are all these things connected? So say you take your graph and your favorite field, you can construct this semigroup, and then from that you can build the semigroup ring. And the semigroup will have a 0, so we want to identify that 0 with the 0 in the ring. And that's called a contracted semigroup ring. And when you build that, you get what's called a cone path algebra. And that's almost a Leavitt path algebra. The only thing that's missing is that CK2 relation that we didn't include. So if you just take that CK2 relation and generate an ideal with it and mod out by that, now you get a Leavitt path algebra. And this is my personal favorite way to define a Leavitt path algebra. Gene kind of gives me a mean look every time I say that, but there it is. And then how does this connect to the C-star algebra? Well, okay, now let's talk about this over the complex numbers. Then there's this obvious map from the Leavitt path algebra to the C-star algebra. You send sort of the vertices to the corresponding functions and the edges and so on, and you get a dense subalgebra there. Okay, so I want to talk a bit about graph C-star algebras. I mean, graph inverse semigroups, because I imagine that's the thing that's less familiar, and also because Piotr asked me to. So where did the graph inverse semigroups come from? So let's back up for a second. If you're studying semigroups, if you encounter any semigroup for the first time, one of the first things you ask about it is what are its Green's relations? And these go back to James Alexander Green from 1951. And these are a way of trying to understand the ideals in the semigroup. So the first one is the L relation. According to the L relation, two elements in a semigroup are related if they generate the same left ideal. And R is likewise if they generate the same right ideal. Two elements are J related if they generate the same two-sided ideal, and then H and D kind of mix L and R. And this is something very, very famous in semigroup circles. Now, for every semigroup, this gives you a whole bunch of equivalence classes of things. And so then it's natural to ask, what sort of structures can you build with that? And this is a question that comes up in the literature over and over. You can ask this about really any algebraic object. Like if you take the subgroups of a group, what does that form as a partial set or lattice under set inclusion? In the case of, you can do this with rings. You can ask about the ideals or prime ideals, and we'll get to that a little bit later. In the case of a semigroup, you can talk about congruences, and you can also talk about these Green's relations. So in particular, what partially ordered sets can you realize as the equivalence classes under one of these relations? And the graph inverse semigroups that I mentioned a second ago, they were invented in order to try to answer a question of this sort. So you notice this goes back to 1975. Graph inverse semigroups were first appeared in this paper of Ash and Hall, and that definition predates both Leavitt path algebras and graph C-star algebras. And so they wrote this paper, they defined graph inverse semigroups, and here's the main result. If you take any partially ordered set, its order isomorphic to the set of non-zero J classes of some graph inverse semigroup.
Wait.
And
Is it obvious that J is an equivalence relation?
yeah, so yes, these are all equivalence relations.
Oh yeah.
And
Okay.
so
Of course. Yes. Yes. Of course it is. Yeah.
each one breaks up a semigroup into equivalence classes, and
Mm-hmm.
these classes are partially ordered by set inclusion. And so you get some kind of partially ordered set. And it turns out that you can realize every partially ordered set as the J classes of graph inverse semigroup, but you just have to throw out zero. Okay, so this is a pretty interesting construction. So I wanna tell you about it. So first you have to understand what these things look like in graph inverse semigroup. So sorry.
If you're around the toilet valve, can you fill that in with grout so that way when that with the beauty ring it looks pretty all completed?
Sorry, I didn't quite understand that.
I'll be out of your way in 1 second. I just gotta, yeah.
I don't see who is speaking. Wait. Well, the only unmuted people are you, I, and Ranga. Ranga is now muted.
Yeah,
I think it was
sorry.
a bit random. Okay, go on, because I think it was a bit random. Sorry. It happens.
Okay, no worries. So if you take a non-zero element in the graph inverse semigroup, as I mentioned, you can write it as a path times an inverse path. And for that element to be non-zero, the two paths have to have the same range vertex. So that's what a non-zero element looks like. So if you take two of those, RS inverse and PQ inverse, so when are they L related? When the inverse parts are the same, for example. And the others are similar. So let me show you how to prove the first one because it's fairly simple. The others are likewise. Some of them are a little bit more complicated. So suppose you have two elements and they generate the same left ideal. So the first thing you can notice is that you can get rid of those non-inverse parts, the R and the P. And the reason for that is because if you take RS and you multiply it on the left by R inverse R, according to our defining relations, gives you a vertex. and that's the range vertex of S. And according to another one of the defining relations, that just gives you S inverse back. So the left ideal generated by our S inverse is the same as the left ideal generated by S inverse, so we can just drop the R and the Q, and we end up with that. Okay, so now S inverse and Q inverse generate the same left ideal. What does that mean? It means that S inverse is something times Q inverse, and Q inverse is something times S inverse. But if you stare at the relations for a little bit, the normal form and everything, that something in both cases also has to be an inverse path. And then you have those two equations. You can take inverses of both sides, and that just gives you that S is a subpath of Q, and Q is a subpath of S. And the only way that can happen is if they're actually the same path.
Yeah.
So that's how arguments like this go. Okay. So now let's look at the J relation. So RS inverse and PQ inverse are J equivalent if their range vertices are in the same strongly connected component of the graph. So strongly connected component means if you take two vertices in it, you can there's a path from one to the other in both directions. In case you don't remember.
Wait. So you wait. So you require that there is a directed path in both directions.
That's right. If you take any pair in any order, there's a path from one to the other.
Because connected just means that there is an unordered path between the two vertices.
Yeah, so if you're in an undirected graph, then connected just means there is a path, right? And strongly connected is a version of that for directed graphs. And there you require this. So the weakly connected would be that there's a path in some direction. And strongly connected.
But also you can use this term connected for a directed graph, because even in a directed graph you can make sense of an undirected path.
Right.
And when you have an undirected path connecting the two, then it's connected.
You can look at
yeah.
You can look at the underlying undirected graph, and there you get
okay, exactly. It's the same thing. It's equivalent.
Yeah.
But it's interesting because this combinatorial connectedness is equivalent in the sense of connectedness given by hereditary subsets thought of generating the topology.
Yeah. Okay. So
that's a quirk,
Yeah. So the J one, that's the one that we're interested in connection with the Ashen-Hall theorem. So two elements are in the same J class if their range vertices are in the same strongly connected component. But if you have a strongly connected component with more than one vertex, that means that now you have to have a cycle in that graph. And so if you start with a graph that doesn't have any cycles, then the J classes there correspond just to the vertices. That's a simple observation, but that's the key to this construction. So let me show you now how to do this. So we start with a partially ordered set, and we need to somehow turn it into a graph. And we're going to do that in the most obvious way possible. So for every point in the partially ordered set, we create a vertex in the graph. And then if you have 2 points in the partially ordered set that are related, we draw an edge from the corresponding vertices in that way. So pictorially, this is what it would look like. If your partially ordered set is just P and Q, P above Q, then for each one we create a vertex and we draw an edge between them in the same order, as it were. And that's just it. So this graph is necessarily acyclic because we started from a partially ordered set, so you can't go back and forth, then you have the same element. And because it's acyclic, that means that the J classes exactly correspond to the vertices. So each J class just consists of elements RS inverse, where R and S end up at that vertex. And then you do a very quick argument to show that when you do this, the ordering is preserved. If you take 2 points P and Q, P above Q in the partially ordered set, and you look at where they go in the graph, well, they end up with these vertices VP and VQ, and there's a path from VP to VQ. And if you play with that for a second, you get that VQ is a multiple of VP, which means that the two-sided ideal generated by VQ is contained in the two-sided ideal generated by VP, and you can go back from that as well. And so that gives you an order isomorphism between the partially ordered set and the non-zero J classes. So that's it. Okay, so now just like with graph C-star algebras and Leavitt path algebras, graph inverse semigroups also turned out to generalize various other kinds of semigroups that had been known before. So I have this graph I've shown you twice now. In the case of graph C-star algebras, that was the Kuntz algebras. And in the case of Leavitt path algebras, this gave you the Leavitt algebras. And in the case of graph inverse semigroups, it gives what are known as polycyclic monoids, which predate graph inverse semigroups.
Hmm.
And then if you just take the one vertex, one loop graph, that gives what's known as the bicyclic monoid. And this one is famous in semigroup circles because this is kind of the canonical example of an inverse semigroup, which is not a group. Every group is an inverse semigroup. But this one, so it's generated by two elements, E and E inverse, and E inverse E is one. That's the defining relation. So E has a left inverse, but not a right inverse. And here
It
I
kind of
have,
looks like an isometry.
yeah. Yeah. So, and that's actually the theme of the first half of my talk, which is these things, to a large extent, developed independently, but there is very similar things that happen in all of them. That's the part two. And I'm just going to tell you this because I found it amusing. In some cases, one inspired another, particularly in the development of Leavitt path algebras. There's been a lot of inspiration from graph C-star algebras, but oftentimes in all three of these areas, you see very similar things proved, except the details are all different, and generally the proofs are all different. But nonetheless, I think it's amusing, so I'm going to tell you about it, whether you like
Zach,
to.
if I might make a suggestion, you still have 1 hour and 8 minutes, so we can proceed slowly. I mean, just don't have to rush.
Yeah, I'm rushing. Maybe,
I
maybe.
think through some arguments and calculations, it could be slower.
So yeah, if I'm rushing, please slow me down in that moment.
That's precisely what I'm doing, kind of. I put like in LaTeX a global command, you know.
Yeah. So yeah, apologies. That's the tendency I have when I
Yeah,
read.
I know, because typically I have 1 hour for your talk. So if you want to say what you want to say, you have to speed up. But
Yeah, it's
remember,
partly.
you are not driving your BMW in Germany. You are driving
eh,
some Rolls Royce
yeah.
in Britain.
Is there anything you want me to go back to or anything?
No, no, it's fine. I mean, the ideas were simple, but I could not follow, for instance, all the arguments letter by letter. It was
Yeah.
too
So
fast.
if I do that again, just yell at me.
Okay, okay.
Okay. Thank you. Okay. So you define some algebra, in this case, a C-star algebra. What's the first thing you ask about it? When is it simple? And that was one of the first things proved about graph C-star algebra. So I want to go through some of the notation here because it'll come up later. So at the top, I'm going to introduce this notation for vertices. We'll say that one vertex V is greater than or equal to another vertex. Sorry, U is greater than or equal to V if there's a path from U to V. And this is not a partial order, it's a pre-order, but nonetheless, this notation is convenient. So here's a description of the simple graph C-star algebras. So for that to happen, the graph in the graph, every cycle has to have an exit, and every vertex has to connect to every infinite path and every singular vertex. So singular means it's either an infinite emitter, emits infinitely many edges, or a sink, emits no edges. Okay, so that's the graph C-star algebra result. And then we have the same thing for Leavitt path algebras. And the condition on the graph is actually exactly the same, but it's stated in different language. And I want to explain this too, just because it's going to come up throughout. So here, instead of talking directly about vertices, we talk about sets of vertices, hereditary and
Mhm.
ZACHARY. So the first condition is the same. Every cycle has to have an exit. And then the second condition is the only hereditary saturated sets are all the vertices and the empty set. So hereditary means that for a set of vertices, it means that if you have a vertex U in that set and it connects to some vertex V elsewhere, that vertex also has to be in the set. And saturated means that if you have some vertex that's regular, meaning it emits finitely many edges and at least one, and it sends all of its edges into the set H, then it actually also has to live in H. Okay, so that's, I believe this was proved a bit differently than the C-star algebra version, but it looks exactly the same.
Can you
So
go back
now,
to the previous slide so that I can compare these two conditions? Okay, so the first one
yeah,
is
I
a
mean, they're stated differently, but you can show that they're equivalent.
okay, so I'm trying to understand number two. So I have a vertex and an infinite path. Okay,
Yeah.
and V must be connected to
I,
every.
I think that's a misprint. V should connect to some vertex along that path.
Exactly, this is what I'm puzzled by. So what do you mean? You mean like the end of EI, right?
It's a misprint. I should have put like range or source in front of that
Yeah, I think
EI.
source would be better because then you have S of E1 and then you have everything.
Yeah. Yeah.
Yeah.
So
Okay,
apologies for
so
that.
I put S of EI. So please remember to correct the typo before you send me the slides. Okay, and number
Okay.
three, for every U in E0 and every, so that's saturation. Okay, so two is for hereditary and three is for saturation, right?
Not quite. I mean,
Oh, you mean then conspire together. Okay.
right. If you have these conditions, then you won't have any interesting hereditary saturated sets. But yeah, you kind of need to treat these infinite paths and sinks sort of
Mhm.
behave similarly in this context for reasons that yeah. don't have a good heuristic explanation, but
Okay. By the way,
sorry.
congratulations on spelling Szymański correctly.
Oh, oh yeah, I try. I try. I'm not gonna. How do you pronounce it?
Szymański.
Szymański?
Yeah, perfect. Very good.
Thank you.
Very good.
Okay, so that was graph C-star algebras. This is Leavitt path algebras. What would be the analog of this for a graph inverse semigroup? Well, in a semigroup, simple is about congruences, right? So simple means you don't have any non-trivial homomorphic images. And in a semigroup, so yeah, do I need to go into what congruences are on semigroups? Maybe just quickly. So congruence on a semigroup is an equivalence relation, and anytime a pair of elements is related, if you multiply both of them on the left or on the right by something else, you'll still have a related pair. And this is what you mod out by to get a quotient. In groups and rings, you can attach that to a normal subgroup or an ideal. But in the case of semigroups, this is the best you can do. It's just a relation that tells you how to conflate elements when you go to a quotient. So when do you have only trivial quotients? Well, when you have the two trivial congruences. So you always have the congruence that relates everything. That's the universal congruence. You mod out by that, you just get a semigroup with one element. And then on the other end, you have the diagonal congruence, and that's the one that relates the fewest things, just every element to itself. You mod out by that, and you get the same semigroup back. And so the analog of simple for a semigroup is
Okay.
congruence
Yes. Exactly. Yes.
you just have these two trivial congruences. And so about 10 years ago, James Mitchell and I described the congruence-free graph inverse semigroups. And, full confession, at that particular moment, I had no idea about the graph C-star algebras, and we weren't even looking at the Leavitt path algebras. This was just a natural thing to do for a class of semigroups. So here usually when you talk about graph inverse semigroups, graph C-star algebras and Leavitt path algebras, you don't allow the empty graph. And some mathematicians, well, yesterday I was hanging out with some universal algebraists, and they really don't like empty structures. But in this particular setting, it didn't hurt, as far as we thought, to allow the empty graph. And if you take the empty graph and you generate a graph inverse semigroup from it, all you get is zero. So it's just the semigroup with one element, and that one is congruence free, but that's a trivial case. And then
But
there's
you know,
another,
I would, Zach, I would defend the empty set because
yeah.
it's a compact house of topological space, and the sister algebra of all continuous functions is exactly the zero sister algebra. And really, when you do any categories, any diagrams, you need it.
Yeah, I agree. I agree. But some people object to things like the empty semigroup, you know.
Okay.
So we don't we don't need to go into that. So there's a second trivial case, and that's just if you take the graph with one vertex and no edges,
Yeah.
the graph inverse semigroup from that you get has two elements, that vertex and then zero. And that's also congruence free. But these are the non-interesting trivial cases. In the non-trivial cases, the condition is that the graph has only one strongly connected component, and each vertex emits at least two edges. So this condition is different from the previous one, only about hereditary and saturated sets, but somehow it has a similar flavor.
But I'm really
Only,
puzzled why two edges. That's very puzzling to me.
at this point, I don't think, this was like 9 years ago. I don't exactly
Yeah.
remember what that does, but yeah, sorry. I can't give you a
Mhm,
quick
mhm, mhm.
explanation for why. But it is some kind of connectedness condition, this. And so in that sense, it's somewhat similar to this one, that there's only the trivial hereditary and saturated sets. Nonetheless, the point is this is a similar kind of result that if you like look at it from very far away, it looks sort of similar, but obviously was proved in a very different way. Okay, so that's the first example of such a thing. Here's another one. So after you've figured out what the simple ones are, what do you next? You look at nice ideals. So in the
Yes.
case of a graph C-star algebra, those would be the gauge invariant ideals, and these are, morally speaking, generated by the vertices. And then there's this interesting result that if you mod out the graph C-star algebra by one of these nice ideals, you get
Sorry,
another.
Zach, may I interrupt you for a second? I just want to throw in a trivial remark for experts, but I think it's interesting for non-experts. You could skip saturated in this first sentence because if you just be hereditary but not saturated, by the sheer fact that you generate an ideal, all these vertices that would be in the saturation of your hereditary set would come up. So the first sentence is true even without the word saturated because it automatically comes up. But
Okay.
by saying that you generate the ideal, IH, from a hereditary set, you throw in all vertices that would be in the saturation of your hereditary set.
Interesting. So when you mod out by this ideal, you get a graph C-star algebra of a different graph. And to build this graph, you throw out all the vertices from the set you started with, and you build what people usually refer to as a quotient graph. But I came to a talk a couple of weeks ago, and Piotr really objected to calling this
Yes,
quotient graph,
very
and I agree with
adamantly.
that. I agree with that. So it's not a quotient graph, and it's not quite a subgraph. You pass to a
Yeah,
subgraph, but then you add in some
yes.
more things corresponding to breaking vertices. So very quickly, let's talk about breaking vertices because they're going to come up again. So a breaking vertex for a set of vertices, usually hereditary saturated, but it doesn't really have to be. So a breaking vertex is an infinite emitter outside of that set, which sends all but finitely many of its edges into that set, but then some finite number outside. So here's this construction, and here's this result. And there is the same thing for Leavitt path algebras, except now the nice ideals are not gauge invariant, they're graded. Leavitt path algebras have this graded structure, which we don't need to go into, but the idea is roughly the same. These are the ideals generated by sets of vertices.
Yeah.
And here you take a hereditary saturated set of vertices, you generate an ideal with that. But for technical reasons, you also have to throw in these elements coming from breaking vertices. And then you build another, I'm not going to call it a quotient graph, but whatever, graph. Here you throw out the vertices and the edges from each, and then you add in some stuff corresponding to the breaking vertices, and then you get a result that looks sort of formally identical. You might mod out a Leavitt path algebra by one of these nice ideals, and then you get a Leavitt path algebra over a different graph. Okay?
May I make a brief comment because it might enlighten a little bit of why we do things in such a way. So the idea with these subgraphs or these extended subgraphs is that you pick up your hereditary saturated whatnot set, and then you kill all the vertices in this set, and you kill all edges that end at these vertices. And this is how you proceed to another graph. And this is how you go from one Leavitt path algebra or one graph sister algebra to another graph sister algebra. But when you have breaking vertices, this recipe wouldn't work. Because why are breaking vertices such troublemakers? The breaking vertices are such troublemakers because when they are infinite emitters in the original graph. But then when you kill this hereditary saturated subsets, these become regular vertices. So the second Kunz-Krieger relation, this one of the sum, has to hold. And it didn't hold before. So somehow you have to kill it by hand. And this is exactly what you are doing.
Yeah, thank you. So as you can imagine, there's going to be a version of this for graph inverse semigroups. So what's that going to look like? So now we have to talk about congruences again, right? So instead of nice ideals, we want to talk about nice congruences. So what's a nice congruence on a semigroup? Those are the Riesz congruences. So these come from ideals in a semigroup. If you take an ideal in a semigroup and you conflate all the elements in that ideal, just send them all to one point, that always gives you a congruence, and those are the nice ones. So in that same paper with James Mitchell, we described the quotient of a graph inverse semigroup by a Riesz congruence, and this structurally looks very much the same. You take the Riesz congruence, so that corresponds to an ideal. You look at all the vertices in that ideal, and then you remove them from the graph. And now what you build is an honest subgraph, rather than one of those weird things where you add and compensate for breaking vertices and all of that. You just pass to a subgraph, and the quotient is isomorphic to the graph inverse semigroup of that subgraph. And again, when we proved this, we really weren't thinking about the other stuff, the graph C-star algebras or the Leavitt path algebras. It just came out, and I think it's amusing that it has the same form. So the proof looks different. I don't want to go into it, but I want to show you a couple of other examples of this phenomenon. So once you've understood, maybe the simple ideals or the nice ideals, maybe you want to talk about all the ideals, or in the case of C-star algebra, the closed ideals. And if you look at all the ideals or all the closed ideals, they form a lattice. And then it would be nice to understand that lattice. And here is some kind of description of that for a graph C-star algebra. So the only place I found this was in this book by Gene Abrams, Perriar, and Mercedes Celis Molina, but I'm wondering if there's sort of precursors of it elsewhere.
Wait, I'm a bit puzzled by your definition of simplicity, because I would imagine that a loop, I don't know why it's so bad to use this term, I mean, a closed path is a loop, is that all these vertices, which are endpoints or start points of edges that build up your closed path or a loop, are pairwise distinct. And I don't see this being satisfied just by saying that S of EI is different from S of E1. That's not quite clear to me that it's enough, because I can go up, I can entangle some I and J, I mean self-cross my path as many times as I want, and then come back to S of E1. So are you sure that this is the definition of a simple path that you want? I mean simple closed path?
I think it's the definition for this purpose. So I copied this from the book. It's possible that I made a mistake, but not that I'm aware of. But I do think this was defined specifically for this result. And maybe in general, simple for a path might mean something different in a different
Let me
context.
draw what I mean, okay? So I have my starting vertex, S of E1. I go, then I intersect, and I come back. Then your condition is satisfied. But I would never call this loop simple.
There
But
is
I
only one.
think this term is used. I have seen that in a few other papers also, Pedro.
Okay, so this is a legit definition. That's what you
Yeah,
mean.
it's just that
Okay.
you don't come back. There is no loop going through this source of E1 many times.
Okay.
That's
Okay. Okay. Thank you.
So you also have to forgive me because I know very little about graph-C-star algebras, and mostly what I have here I looked up for this talk. But what I want to point out here is that this description of the lattice that they gave, so they write down this other lattice where the elements are these triples. The first bit is a hereditary saturated set of vertices. The second bit is a certain set of cycles. And the third bit, in this case, is something that connects them. And here it's a non-empty proper compact subset of the unit circle. And you have to turn that into a lattice. So you have to define an ordering on these triples, and it's slightly complicated. I didn't put on the slide, but they do that. And then they show that this lattice is order isomorphic to the lattice of closed ideals of C-star algebras, this time under obvious operations, intersection and ideal addition. Okay, so in this case, I think the Leavitt path algebra result actually might predate this. So in the same book, they have a very similar thing for the lattice of all ideals of a Leavitt path algebra. So I should mention here, this result is just for row finite graphs. That means you only have finite emitters. And they say that they did it for row finite graphs just for notational simplicity, but in theory, these principles should apply to all graphs. In the case of a Leavitt path algebra, they did it for...
Wait. Can you go back for a second?
Yes.
So these are assumptions. So what is the claim? The theorem is the claim, right?
Yeah, the theorem is only for row finite graphs.
Okay.
But they say that something like this should be true for all graphs. It's just that the notation would get much worse. That's what they say.
Okay. It's a lame excuse.
Yeah. In the case of Leavitt path algebras, that's not as much of an issue. So here's the result for Leavitt path algebras. This is all graphs. The lattice of all ideals now is order isomorphic to this lattice of, again, ordered triples. And the details are all different, but sort of from 1,000 feet away, sort of similar. The first component is a hereditary saturated set of vertices, but now plus some breaking vertices. The second component is again a set of cycles, but now with some other conditions on it. And the third component is a set of polynomials which connect the two. Okay, and on this slide, I also put Ranga's general description of an ideal in a Leavitt path algebra, just for reference. This is how you would describe any ideal. You start with a hereditary saturated set of vertices plus some breaking vertices, and then some pieces coming from cycles.
May I ask you a stupid question? So whenever you have closed ideals in C-star algebras, what is beautiful about the lattice of such ideals is that it's always distributive. Now, I know Leavitt path algebras are just dense subalgebras, but they are extremely regular. They have, for instance, in many cases, the same K-theory, which for me borders on a miracle. But what can you say about the distributivity of such lattices of ideals in Leavitt path algebras?
Yeah, this is something that Ranga also proved. The ideal lattice of a Leavitt path algebra is distributive.
Wow, cool,
Yeah.
wonderful. Wonderful. I mean, this is absolutely amazing because this is a very non-algebraic property. That's a sister algebraic property.
Yeah.
So that Leavitt path algebras enjoy the benefits of analysis is really cool.
Yeah. Okay, so graph inverse semigroups. So there is a vaguely similar result about graph inverse semigroups due to Luo and Wang from about 4 years ago. So here we're not going to be talking about ideals, we're going to be talking about congruences, and congruences also of a semigroup also form a lattice under appropriate operations. And they describe the lattice of congruences on a graph inverse semigroup using, again, these triplets. In this case, the first component consists of a hereditary set of vertices. The second component is this other set of vertices. They're sort of morally correspond to breaking vertices. And then the third bit is a function on cycles that kind of says something about the original set of vertices. So again, the details aren't terribly important for my purposes. I just want to note that it's interesting that it's a classification of the analogous object here, the congruences, and it's a classification in terms of triples consisting of vertices and cycles. And of course, it was proved independently, separately, and using different methods. But there it is. So I hope you find that as amusing as I do.
Yes. Yes.
And I want to give one more sort of instance of this sort of. This one is not a perfect analogy this time. So in the case of graph C-star algebras, there is a classification of the simple ones. I didn't put the whole classification here, just one piece in the purely infinite case. And here, using K0 and K1, you can classify these things. You can describe when they're isomorphic and when they're Morita equivalent. And in the case of Leavitt path algebras, people really tried to do that and couldn't. So some simple Leavitt path algebras are perfectly well understood. Like if you take an acyclic finite graph, then the Leavitt path algebra of that will be some kind of matrix string or a product of matrix strings. And if it's simple, just a matrix string. And then, of course, we know what that's isomorphic to and Morita equivalent to. But the piece that no one has so far been able to work out is what happens if you take two Leavitt path algebras that are simple and purely infinite. And purely infinite here means something slightly different from what it means for graph C-star algebras. People here, what we have is just a famous question. This is probably the most famous open question about Leavitt path algebras. If you take two such Leavitt path algebras, and their K0 groups are isomorphic, and the isomorphism respects the equivalence class of the identity, are they the Leavitt path algebras then isomorphic?
Okay, let me stop you here. So, for starters, how does it relate to the Hazrat conjecture?
Okay, here's the Hazrat conjecture. Well, there might be several, but this is the famous one about Morita equivalence. So again, there's a bunch of results on isomorphism and Morita equivalence in Leavitt path algebras, but there's maybe more questions than answers. So
my second question is really dummy. How about K1? Why don't you need K1 in with Leavitt path algebras?
I'm sorry, I couldn't tell you. At the conference where we were, I think Efren Ruiz gave a very good explanation for why K1 doesn't matter for path algebras, but I don't know enough about that to go into it, unfortunately.
Because there is a very beautiful result which I was using. It's by my uncle, Mikkel Rordam, I believe. Anyway, this area that you can actually classify graph sister algebras, which they must be simple and a bunch of some other conditions. Graphs have to be regular, probably. Stuff like this. So there are lots of restrictions, but still there are many interesting cases happen like the Kunz algebras, okay? But it's fascinating that for this class of graph sister algebras, if you know K-theory, And if you know the class of one, you know the sister algebra.
Mm-hmm.
Yeah, and it's uniquely determined. But and if you don't know the class of one, you only know K theory, then the two guys are Morita equivalent.
Yeah, it's pretty amazing that result. And
Yeah,
I personally haven't.
this is fantastic because you see,
Yeah,
why is it fantastic? Because when you have graph sister algebras, the K theory is on the plate. I mean, a high school student can compute it from a graph, or maybe
yeah.
a kindergarten child. It's just coming from a graph. I mean, you look at the graph and K theory. It's served to you on a silver platter. It's a bit more tough to compute the class of one because it's some linear algebra over integers, but it's still a kind of AI task.
Yeah. So I should say something about the Hasrod conjecture. So this is for graded Morita equivalence. So Morita equivalence is about categories of modules being equivalent, and Roosbay is the expert on all things graded. And so you can talk about categories of graded modules with graded equivalence between them. And we don't need to go into the details of that, but his is not just a question, it's a conjecture
Yeah.
that two Leavitt path algebras from finite graphs with no sinks are graded Morita equivalent if and only if the adjacency matrices of the graphs are shift equivalent. Okay, so that's sort of the corresponding picture for Leavitt path algebras. So in the case of graph C star algebras, there is a classification, a very intricate, kind of difficult one. In the case of Leavitt path algebras, there's more questions than answers. And in the case of graph inverse semigroups, everything is known and it's relatively straightforward. So, about 20 years ago, Krieger proved that two graphs are isomorphic in the appropriate sense. I put that at the top, if and only if the corresponding graph inverse semigroups are isomorphic. And then Costa and Steinberg proved that that's equivalent to the graph inverse semigroups being Morita equivalent. So for semigroups, this might be less familiar, but there's also a notion of Morita equivalence, which is inspired by Morita equivalence from rings. And here, instead of talking about categories of modules, you have categories of sets on which these semigroups act, and they're equivalent. That's what this means. And then Roosbay wanted a graded version of that. That's what he likes. So we came up with a notion of graded Morita equivalence, and we showed that graded Morita equivalence for semigroups always implies Morita equivalence. And so for graph inverse semigroups, that's also equivalent. And so it's as clean as it could possibly be.
But wait, what is the grading for semigroups? By the length of a path or the word in your semigroup?
So in general, grading on the semigroup means it's a certain function to a group, just like in the case of rings. In the case of graph inverse semigroups, the grading is exactly the same. You send each path to its length and a
Okay,
ghost path to the
that's what I
negative length.
thought. Yeah.
And that grading induces the grading on the Leavitt path algebra.
Yeah. Okay. Cool. Cool.
Okay.
And is it the same Krieger from Kunz Krieger?
I don't think so, but
No.
I'm
So
not
it's
totally
not
sure.
Wolfgang Krieger.
It,
You have Kunz
it just
Krieger conditions, so it's only fair
it
to ask
just
if it's the same
just
Krieger.
might be. It just might be, but I'm sorry. I don't
Okay.
remember. Yeah. Okay. That part three. Now I want to talk about something in more detail. Um, so here's, I showed you this before. This is where graph inverse semigroups came from. It was in order to try to construct partially ordered sets with desired properties from semigroups. Now, this question, as I mentioned, you can ask for anything, and in particular, you can ask it for rings. If I give you a partially ordered set, can you realize it as some class of ideals in a ring? Now, if you're just talking about all ideals in a ring, those will form a lattice. And so you certainly won't be able to realize any partially ordered set. However, if instead of talking about all ideals, you look at just prime ideals, then that really opens things up because that's not going to be a lattice. And in theory, you might be able to get any possible partially ordered set. Well, not any possible. There'll be restrictions, but it doesn't have to be a lattice anymore. And so there's a long history in the ring theory literature of looking at this question. If you look at the prime ideals, what structure does that have as a partially ordered set? And in the case of commutative rings, the prime ideals also have a nice topological structure. So
That is
we're yeah. So there's this language, talking about the spectrum of the ring. That's the prime ideals with this topology. So that's where that goes back to.
so.
And
Another silly question. In commutative rings, every maximal ideal is prime. In non-commutative rings, is the same true?
yes,
Okay.
I put the definition of prime ideal at the top here in a non-commutative ring in case you don't know what that means. So it's a generalization of the
Yeah.
notion of prime commutative rings. Um, so in this particular question of partially ordered sets, prime spectra as partially ordered sets, the person most famously associated with that is Kaplansky. And he published a book in 1970, and he goes into this question in some detail for commutative rings, commutative unital rings. And he showed that um, the prime spectrum of a commutative ring as a partially ordered set has certain properties. So any partially ordered set that you hope to realize this way would also have to have them. So the first property is this: every chain has a greatest lower bound. And the reason for this is that if you take a chain of prime ideals and you take the intersection, that's also going to be a prime ideal. And so every chain has to have a greatest lower bound. And the same thing for least upper bounds. If you take in a commutative ring a chain of prime ideals and you take the union, you get another prime ideal. And the third condition is kind of interesting. I'm going to refer to it as the Kaplansky condition, and it's a discreteness property. It says that if you take two prime ideals, P and Q, P properly contained in Q, then between them you have to find two more ideals, P prime and Q prime, so that between those there's no prime ideals. So between any two prime ideals, there's a discrete step.
Ha.
And I'll tell you a bit later why this is. So Kaplansky played with this quite a bit, and there's pretty extensive literature on this kind of thing in commutative rings. So I'll just give you a sampling. Lewis showed how to realize every finite partially ordered set as the prime spectrum of a commutative ring, and he and Ohm characterized the partially ordered sets that are order isomorphic to prime spectra of Bézout rings. And this one's kind of interesting because it's those same three conditions that I showed you before: greatest lower bounds, least upper bounds, Kaplansky condition, and one more. The partially ordered set has to be a tree. And I'll show you one more. Here's one from Fachini. He described the partially ordered sets that are order isomorphic to prime spectra of generalized Dedekind domains. And again, I don't want to get into the details of this, just to show you that there's some literature on this. So what I want to do is look at this question in non-commutative rings. And this is how we'll get back to Leavitt path algebras in a second. So if you look in the prime spectrum of a non-commutative ring, does it have to satisfy those three conditions that Kaplansky wrote down? So let's take them one at a time. So the greatest lower bound condition, yes, that carries over. And you can actually prove it not just for chains of prime ideals, but for downward directed sets of prime ideals. That means that if you have two ideals in such a set, in their intersection, there'll be another prime ideal. It turns out that this condition, that every downward directed set has a greatest lower bound, is actually equivalent to every chain having a greatest lower bound, but we don't need to get into that either. But I thought I would show you how to prove this because it's a nice ring theory argument. And
Sorry,
if
can you help me imagine something which is downward directed but it's not a chain?
so it just means that if you take two points, they might not be necessarily related to each other, but
Uh-huh. But
below
there's something
them,
below.
there's something below both of them.
Okay. Okay.
That's what you should picture for
Yeah, yeah,
downward
yeah.
direct. Yeah. So here's how this goes. So we have this set of prime ideals downward directed. If you take their intersection, that will be a proper ideal because individually they're proper ideals. And so, because to be a prime ideal, it can't be the whole ring. That's the point here. So now we just have to show that this intersection is a prime ideal, and then we'll have our greatest lower bound for our downward directed set in the spectrum. So to do this, let's take two elements, x and y, and suppose that x, our y, is contained in this intersection. And now we just need to show that either x or y is contained in P, and then we're done. So suppose that x is not. Let's try to show then that y has to be. So if x is not contained in intersection, then it's not contained in at least one of those PIs. So let's set that aside. And now let's take any PJ, any element in I, J, and intersect it with PI. So in that intersection, there'll have to be a prime ideal by the setup. And that prime ideal still contains x, r, y because that's in the intersection, but it doesn't contain x because that's not an I, PI. But PK is a prime ideal, so if it doesn't contain x, it has to contain y. And so then that y is now contained in PJ, but PJ was arbitrary, and so the whole intersection has to contain y. And so it's prime. And then we're done. Okay. So I like that argument. So that was the greatest lower bound condition. That carries over to non-commutative rings. What about the least upper bound condition? That one does not. So there's an example due to my advisor, George Bergman, which shows this. So you just look at the free ring on two generators, and in it, you can write down this chain of prime ideals. I put that here. And then you can show that if you take the union, that's not prime and it's not even semi-prime. So that second bit breaks down. And what about the third condition, this Kaplansky condition? Well, that one we have no idea about. So this is currently my favorite open question about non-commutative rings. Is there a non-commutative ring whose prime spectrum does not satisfy the Kaplansky condition? If you solve it, I'll buy you a beer.
Well, but it must be a very good beer.
Anything you want.
But
Okay.
I find this Kaplansky condition very fascinating. That's a very subtle looking condition.
Yeah.
It's not something I would expect. But wait, so you are saying that for commutative rings, we know it, that Kaplansky is always satisfied, right?
Yes. Yes. For every commutative ring, the Kaplansky condition holds for the prime spectrum.
And
But
how did George come up with this example? How did he reason to get this example?
I have no idea. This was before my time. I never
Okay.
asked him about this. You can actually build an example like this with Leavitt path algebras, and we did. But this one, I don't know. It's simpler to state, and I wanted to mention him.
Okay.
Now Leavitt path algebras are a very nice platform for exploring conditions like this because remember, graph-C-star algebra, graph inverse semigroups came from this kind of thing, and Leavitt path algebras likewise come from graphs, and from partially ordered sets to graphs. That's a short connection. So we thought, hey, let's explore this kind of thing with Leavitt path algebras. And by the way, as far as I know, no one has done this with graph C-star algebras. If somebody has, please let me know. If nobody has, then somebody should, I think. But that's an aside. So let's try to play the same game now with Leavitt path algebras as we did with graph inverse semigroups. So here's a very, very simple partially ordered set. So let's write down the corresponding graph as in the Ashen-Hall theorem. We just, turn the points into vertices and draw an edge if there's a connection. What does the prime spectrum of that Leavitt path algebra look like? Does it have 2 points? Well, no, it doesn't. This Leavitt path algebra is just a matrix ring, and so it's simple. and the only prime ideal there is 0. So that doesn't quite work. But if we tweak that just a little bit, then it does work. So what we're going to do is instead of we're going to take two vertices again, but instead of drawing one edge between them, we'll draw infinitely many edges. And what that does is it nullifies the CK2 condition for
Yeah,
the top
precisely.
vertex. So if you do that, then you actually get a ring with two prime ideals. There'll be the 0, 0 will be a prime ideal, and the ideal generated by VQ will also be prime, and it will not contain VP because we can't get from VQ to VP because VP is no longer regular and we don't have the CK2 condition.
And you can also very easily say what it is in terms of Leavitt path algebras or graph sister algebras. If you are talking graph sister algebras, then you have minimal unitization of compact operators, which is just the Podlesh quantum sphere sister algebra. And the ideal you are talking about is just compact operators. If you want to be algebraic, well, then you simply have minimal unitization of the algebra of infinite matrices. And then your ideal is the ideal of all infinite matrices.
Thank you. So let's take this construction and see how far it goes, right? So it works on this graph, on this partially ordered set with 2 points. Does it work on every partially ordered set? Let's try it. So for every partially ordered set, we're going to define this graph EP. So again, we put in a vertex for every point, and then we put in infinitely many edges between every pair of vertices that come from a related pair of points. So pictorially, this is what it looks like. Does it work in general? Well, to do that, we have to look at prime ideals in the Leavitt path algebra, and there's a classification. Once again, thank you, Renga. This is what all the prime ideals in the Leavitt path algebra look like. Now, there's quite a few complications here, but most of the complications in this statement have to do with cycles and breaking vertices.
Yeah.
And so if you happen to have a graph that has no cycles and no breaking vertices, then this simplifies quite a bit. For such a graph, an ideal in a Leavitt path algebra is prime if and only if it's generated by a hereditary saturated set of vertices, such that the complement of that set is downward directed. And here, downward directed is in graph terms. I put the definition of that in point 1, and it is what you would imagine. It means that if you take two vertices, you can find a third vertex to which they both send paths. So it's inspired by downward directed from partially ordered sets. Now, these graphs that I just constructed are indeed acyclic, and they have no breaking vertices because anytime a vertex sends a path or an edge anywhere, there's infinitely many edges doing the same thing. So there's not going to be any breaking vertices. And so that characterization applies to this class. And then something kind of interesting happens. If you take any partially ordered set, you can write down this function from it to the prime spectrum of the Leavitt path algebra. So what you do is you take the vertex corresponding to the point, and you look at what we call the tree of that vertex. So that consists of all the vertices that send paths to it. And then you take the complement of that in the set of vertices, and you use that set of vertices to generate an ideal, and that always ends up being prime. So this gives you some kind of function from the partially ordered set to the prime ideals of the Leavitt path algebra. And this is always an order embedding. So any partially ordered set you can embed into the prime spectrum of a Leavitt path algebra. And you can describe precisely when it's an order isomorphism. That happens exactly when the partially ordered set has no infinite descending chains.
Zach, sorry, could you please remind me the definition, the construction of this graph EP? So I have a poset. How do I get a graph?
So it's like this. For every point in the poset, you write down a vertex. And then if you have 2 points P and Q, so that P is above Q, you write down infinitely many edges. From
Infinitely
VP.
many edges.
Infinitely many, right? So we don't have to worry about breaking vertex. Well, we don't have to worry about CK2 condition, essentially. That's what that does. Yeah?
Okay, so every element in a poset is an edge, a vertex, and then you have edges which go infinitely many edges which go. Okay, okay. Thank you so much. Just a reminder. Okay, thanks.
Let's see.
And when you have these slashes in this proposition, does it mean that this was a separate independent work, or is it a joint work?
Sorry,
We have these slashes in the proposition between
yeah, so
names.
this is one. So we wrote two papers on this subject. So the first paper is with Gene Abrams, Gonzalo Rondopino, and Chris Smith, and then there was a later paper with Ranga and Barry Greenfield and Gene Abrams. But yeah, so this is one paper.
Okay.
Yeah. So let's see. If I start running out of time, let me know.
We have
But
20 minutes.
yeah, I thought I would tell you a little bit about a few more details about this. If you want to see them, if not, I can skip this. Um, okay, so take a point in the partially ordered set and look at the corresponding vertex in its tree. So that's clearly downward directed because all the vertices there point to the same vertex. And if you take the complement of that, it's clearly hereditary because the complement consists of all the vertices that don't point to VP. And if you have something that doesn't point to VP, but it does send the path to some other vertex, certainly that other vertex can't send the path to VP. So that's pretty simple. And because of that, that complement, the ideally generates is prime. That's just the criterion I showed you a second ago. And then it's pretty easy to see that the ordering is preserved. So if you take 2 points in the partially ordered set, P above Q, and you look at the corresponding vertices, certainly they're related in that sense, just because that's how we define things. And if you now pass to the trees, that relationship gets flipped, right? Because if a VP connects to VQ, then how does that go? Everything that connects to VP also connects to VQ. That's it. And now take the complement of that. That again flips the relationship. And if you don't just take the complement, but also look at the ideals generated, nothing changes. And the reason for that is if you take one of these ideals generated by a hereditary saturated set of vertices and you intersect it with the set of vertices, you just get exactly the same vertices back. So passing to ideals doesn't add any complications. And so this gives an order embedding, this assignment. The downward directed bit, that takes quite a bit more work, so I won't go into that. But that's at least the idea for the construction. Okay, so here it is, right? So now we understand completely what happens with partially ordered sets that satisfy the descending chain condition. We can realize them as prime spectra of Leavitt path algebras. And the interesting question becomes, well, what happens if you start with a partially ordered set that doesn't satisfy DCC? You can still embed it into the prime spectrum of Leavitt path algebra by using this construction, but then you get extra stuff because it's an order embedding, but not an order isomorphism. So what's that extra stuff that you get? Well, if you recall, we can look to Kaplansky for inspiration. In the prime spectrum of a ring, and this commutative or non-commutative, every descending chain has a greatest lower bound. And so when we took our partially ordered set that had infinite descending chains and we sent it into the prime spectrum of Leavitt path algebra, at minimum, we have to pick up along the way greatest lower bounds. So maybe that's it. Is that it? So let's try to play with that. So in order to understand that better, we defined this operation on partially ordered sets that adjoins greatest lower bounds to downward directed sets with no bounds. But you have to do that a little bit carefully, right? Because if you take two downward directed subsets of a partially ordered set, they might actually have the same greatest lower bound if such a thing exists. So to make sense of that, we define this equivalence relation on partially or subsets of a partially ordered set. So we'll say that two subsets are equivalent if you can take any point in one of them and it's above some point in the other. Okay. And if that happens, and those two things are going to have a greatest lower bound, it better be the same greatest lower bound. This gives an equivalence condition. And so here is the construction. Take a partially ordered set, and we'll construct a new thing from it. I'm going to call it AP. What we do is we throw in a point for every equivalence class of downward directed sets with no least elements. And then we're going to try to force that to be a greatest lower bound. And so we extend the operation from the partially ordered sets P to this new thing, AP. A is for adding. And you do this in the obvious way. So if you take a point in the original partially ordered set, P, and then one of these new points, let's say XS, when is that new point XS going to be above P? When all the points in the original set S are above P, and similarly in the other cases. So this just gives a set with a binary relation, and you might ask, does that give you a partially ordered set? And it does. And so we managed to show that this construction gives a partially ordered set, and it's exactly what you get from the prime spectrum of our Leavitt path algebra.
Just wait a second, a stupid question. What is an X in this XS? It's just a symbol, right? You could just write the class of S.
Yeah.
Okay.
So for the class of S, we add a new point to the partially ordered set. And I'm just calling it X.
And this union between P and the rest is kind of disjoint union because these are different animals.
Union. Yes,
okay.
It's a disjoint union. Yeah. So I can't say too much about the proof of this because it's pretty lengthy. But one thing that's kind of interesting about this is that so the way we showed that AP is partially ordered is by showing that it's order isomorphic to the prime spectrum of a Leavitt path algebra. So we wrote down this bijection between the two and showed that it's an order isomorphism. And because the prime spectrum of a ring is partially ordered, this thing also has to be. Okay, so we created this operation on partially ordered sets that adjoins greatest lower bounds. And you can imagine its inverse, which removes those things. So let's call that R. Take a partially ordered set, R of P. We'll just extract all the points that are not greatest lower bounds for downward directed subsets with no least elements. This thing is a partially ordered set. That's pretty easy to see. Using this, we can come up with other descriptions of partially ordered sets that we can realize this way. So let me first give you a little illustration. So here's a nice chain. Just take all the rational numbers of the form 1 over n, where n is a positive natural number. So that's just a nice partially ordered set, a chain. It's downward directed in particular, and it has no least element. So I defined this notion of equivalence on subsets of a partially ordered set. So what does it look like here? What's equivalent to P? Well, really any infinite subset of it, or any subset that has no least element. So that's what that equivalence relation does here. So say we want to do the A operation to it. What's it going to do? Well, it's going to add one more point because there's only one interesting equivalence class here. And then what if we follow that up by R? It's going to remove that point. Okay. But what if you do it in the other order? First you do R. R will do nothing to this partially ordered set because there are no greatest lower bounds for downward directed sets with no least element. And if you follow that up by A, you add one more point, so you get something different. So in general, A and R don't commute. It's like a one-sided inverse. But with that in mind, we came up with a few descriptions of the partially ordered sets that can be realized as prime spectra of Leavitt path algebras using our construction. So they're precisely the ones that are A of something. And another way to characterize them is that they are ones where if you do R and then A, you get the same thing back. And another way to characterize them is that they're partially ordered sets on which R and A commute. And then we wrote down kind of closed description of the partially ordered sets that we can realize using this construction. So first of all, they have to have that greatest lower bound condition. Certainly any partially ordered set that's realizable as the prime spectrum of a ring has to have that. And then there's a couple of other conditions that are slightly technical. I'll talk about them a little bit more in a minute.
Okay, Zach, let me stop you for a second. I'm staring at your condition number one,
Mhm.
and okay, I can appreciate it that the whole business is field independent. But
Mhm.
now, a very stupid question. Can I have a graph that is not of a form EP for some poset P?
Um,
Or
yeah,
is it
certainly.
too? Yeah,
Yeah, yeah,
you can have a graph which is not.
oh, yeah, yeah.
Okay,
This is a very particular class of graphs. So in particular,
okay,
they're acyclic and they have no breaking vertices. So yes,
okay, okay, okay. Great.
this
Because you see, I was wondering why you write EP prime instead of just E for some graph E. But okay, I understand it. But it's actually
yeah,
far more
so
subtle.
we don't have a complete classification of all the partially ordered sets that can be realized as prime spectra of low path algebras. We have it in some cases, but not in total generality, right?
And
So
tell me, in practice, in real life, how far is P prime from P?
so if you just want to realize P, you
Yeah.
take P to be P, right? But here what I'm saying is suppose P is order isomorphic to the prime spectrum of some Leavitt path algebra constructed in this way from some partially ordered set, maybe a different one,
Uh-huh.
right? Suppose that happens. What can you say about
Ah,
P?
okay. I've got you, because it's about the equivalence of conditions. Okay.
Yeah,
Yeah. Thanks.
yeah.
Okay, I'm with you.
Okay, but now if you look at that condition five, right? So we can realize a very wide class of partially ordered sets as prime spectra of Leavitt path algebras. In fact, I think this is the most expansive result
Yeah.
of this in the literature. But you stare at that and you start asking questions. Well, are these three conditions necessary to be realizable as the prime spectrum of a ring or a prime spectrum of a Leavitt path algebra? So certainly the first one is. The last one we don't know. And the second one is not.
Mhm.
Uh, Let me talk a little bit about them individually. So this condition DC says that if you have a downward directed set and you have some regular point, which is above the greatest lower bound for S, then it has to be above some point in S. And regular means it is not the greatest lower bound for a downward directed set with no least elements. So this condition is there are Leavitt path algebras even that don't have it. So I'm
Aha.
out of time, so I won't go through the details of this. But if you write down this graph and you look at the Leavitt path algebra of that, the prime spectrum looks like this. There are two chains, and they both have the same greatest lower bound, but then otherwise they're incomparable. And so this is an example of a Leavitt path algebra prime spectrum that does not satisfy DC.
So sorry, so could you go back to the previous slide? So what is special again before?
So here the
No,
prime idea
previous slide.
here.
Okay, because here you have it satisfied, so you must be in some special. Okay, so you have.
Right. So the graphs EP that we constructed, they all satisfy this TC
Okay,
condition.
because they are the special form graphs. Thank you. This is what I
Yes.
wanted to
Yes.
understand. So that graph that you drew is not coming from an poset.
Right. So this one, for example, in our construction, every point is an infinite emitter, and here none of them are. Right. That's one
Yeah.
difference.
Yeah. Okay.
Right. Okay. Uh, the more interesting one is this DD condition. So it's some kind of discreteness property. So if you have a downward directed set, then you can find another downward directed set that has the same greatest lower bound, but it consists only of regular elements, ones that are not themselves greatest lower bounds for downward directed sets. This one, what's interesting about it is that it's related to the Kaplansky condition. And we showed that under some hypothesis, they're equivalent. And in particular, if you look at a totally ordered set, for a totally ordered set, these two conditions are exactly the same. And so from there, we didn't have any hope of completely describing all the partially ordered sets that can be realized as prime spectra of Leavitt path algebras, but we thought, well, in the case of totally ordered sets, maybe we can, and we did. So that's where I want to go from here, looking at rings with totally ordered prime spectra. So you can show that that happens if and only if every semi-prime ideal is prime.
Or
I
can you
think
remind me what semi-prime means?
semi-prime means that so the definition of prime was if x or y for any two elements x is contained in the ideal, then either x or y is contained in the ideal. And
Yeah,
semi-prime is instead of x and y, you take the same element. X or x is contained in the ideal, then x has to be contained in the ideal.
X are X, you said,
Yeah,
right?
yeah, yeah. So prime is more general.
Mm-hmm.
You take two different elements. Semi-prime is if it's the same element.
Okay,
Or,
okay, okay, I got
um,
you.
yeah, there's other ways to characterize it, but so I think I'll skip this in the interest of time.
You have
Um,
4 minutes.
right. So, but you see, there's the semi-prime business. So the next thing then we had to do was go and describe the semi-prime ideals in the Leavitt path algebra, and we did that. And it turns out that they have this interesting property that they form a complete sublattice of ideals in a Leavitt path algebra. So in particular, what this means, if you take a bunch of a chain of semi-prime ideals and you take their union, you get another semi-prime ideal. In general, that's not true, but in Leavitt path algebra, it is. And this allowed us to show some interesting things in that case. So it turns out that if you have a Leavitt path algebra whose prime spectrum is totally ordered, then it has to satisfy the Kaplansky condition. And again, I wrote down the proof of this, which is kind of interesting because the proof is actually Kaplansky's original proof, more or less. But maybe we'll come back to that. I'll just get to the punchline of this. This is the main result of the second paper that we wrote. And we classified the totally ordered sets that can be realized as prime spectra of Leavitt path algebras. And they're exactly ones that satisfy the greatest lower bound condition and the Kaplansky condition. And but ultimately that leaves this question. Is there a ring out there whose prime spectrum does not satisfy the Kaplansky condition, and maybe a totally ordered one if you like. So that's the conclusion I wanted to get to it. But if in the remaining 3 minutes you want me to go back and talk about some of these details, I could.
It's actually 2 minutes.
2 minutes. So yeah. So in that case, officially, I'm going to quit. But if you want to see some of that stuff,
Yeah.
let me.
Okay, Zach, thank you so much. Thank you. Okay, guys, questions. Łukasz, any questions?
Yeah.
Take your mic. Yeah.
Yeah, I have one. If you could come back to the slide where you talk about the DD condition. Yeah, this one. When I read it, I got the feeling that in the proposition you assume the GLB and DC from the previous ones, and then you get this equivalence. And also previously you said that DC is unnecessary for the theorem from the previous slide. Is this something deeper, or am I overthinking it?
No, so here in this proposition,
Yeah.
we're looking at actually where it says to satisfy the greatest lower bound condition, and then another condition which is very similar to DC but not quite DC.
Okay,
Uh,
so where does it differ? Because while I was listening to your talk, I got the impression that this was exactly DC, and I got a bit confused.
Right, so here, if you look at the statement of DC, for every downward directed subset and every regular P that lives above the greatest lower bound, it lives above
Okay.
some point. And here it's every P, so it's not just
Oh,
every regular.
okay.
So it's
Okay.
slightly stronger.
So
Yeah.
that's the subtlety that I missed. Thank you very
Every,
much.
yes, every. Okay,
Yeah, so there's
Mhm.
sorry, go on.
No. Any further questions? Anybody? Please fire at will. Come on, guys. Tomek, Adam, Riles, Ali. Nobody?
I don't
No,
have a
thank you.
question, thank you.
I'm good.
I have a
Okay.
question.
Go ahead, Riles. But make sure that we can hear you because the sound quality is a bit strange.
Okay, can you hear me now?
Oh, yeah, now it's fine. Yes.
Okay. So could you try to use instead of left path algebra of this Hall graph, use the compact algebra? Because then you don't have the Kunst-Krieger relation to worry about, so you have more ideas to consider.
Yeah, so cone path algebras, this is in the Leavitt path algebra book. They show that every cone path algebra is a Leavitt path algebra.
Yeah, sure. But instead of looking at this new graph EP, could you just use the Hall graph and then consider the compact algebra of this graph to consider the Posets
Potentially, yeah.
relations?
Yeah, maybe. So there's also other ways of kind of simplifying the construction to get rid of the Kunst-Krieger relation. Another way, rather than putting in infinitely many edges, you can put two loops at every vertex, and that accomplishes more or less the same thing. But yeah, potentially you could. I think we went with Leavitt path algebras because there were all these classification results about, prime ideals and so on and so
Yeah.
forth. We just, relied on that.
Yeah.
But and okay, cone path algebra sort of came along later for the ride, but I had an office next to Gene's and he was into Leavitt path algebras. And actually, honestly, where this started, so this is with Chris Smith. At that time, we had the seminar, and one day he just came in and well, what did he do? He drew this,
Mhm.
and so we just went from there. But that's the history of it.
But maybe, I don't know, maybe the spectrum of the simple, just one edge graph of the compact algebra is just also isomorphic to the
Yeah, it
original
might be.
concept.
It might be. Yeah.
Because then you don't have to remove a second Kunst-Krieger relation. It's not there.
No,
Yeah.
I mean, if you consider the compact algebra, you could just consider just one edge
Yeah,
instead
that's what I'm
of
saying.
this
Yeah.
new graph.
Yeah, and then maybe you can even use results about graph inverse semigroups. They're more applicable to cone path algebras
Yeah.
than Leavitt path algebras.
By the way, since I see Gilles, let me just mention that we are looking at path homomorphisms of graphs to have a very nice category from which we have a functor to Leavitt path algebras and graph sister algebras. But at a certain moment, we realized that we need something more general than what we had before, given just in terms of graphs. We realized that in our formulas we need to use adjoints or ghost edges, if you will, and we are now formulating this broader category using inverse semigroups, which is exactly the reasons why I asked you to talk about inverse semigroups. Yeah, so that's what we do with Gilles and Mariusz Tobolski. Okay, guys, any other questions? Ranga, maybe you want to ask your colleague from Colorado Springs. But you would have to unmute yourself. Okay, since there are no further questions, let us thank Zach for... Oh, you're unmuted. You can speak now.
Okay. Yeah. No, it's fine. I have no questions. Thanks, Zach. So, as always, very nice talk. Appreciate it.
Yes, I agree. Let us thank Zach again for a very, very beautiful talk. Thank you, Zach. Now let me stop recording, but please don't go.